at that time, I quickly went over a slide that had some graphs on it. So I want to review Ohm's law, and I want to show you what a resistor, what its graph looks like when we make a graph of its voltage and its current, all right? Because we can graphically represent this. That's what this is all about. It's going to take me about 5 minutes. Then we're going to talk about the lab, and I'm going to teach you how we connect meters into circuits so that you can measure some information, measure some volts and some amps, so that we can study a resistor and a lamp. All right, we want to treat them as loads, and we want to see how they behave. All right, so I just want to, again, make a video of it. That's why I'm writing it on here. So I'm again going to just start with Ohm's law. Ohm's law. All right, so you can put that on there. That's our note for today that we're going to roll on with. And remember, Ohm's law states that the resistance in ohms is equal to the voltage over the current. And we did some practice work. You guys took a picture of that work. You submitted it. Awesome. Okay? And what it says is that there's a relationship between the V and the I. If the voltage is increased in a circuit, all right? If we make the voltage higher, remember, it's like water pressure. If we make the water pressure higher, what will happen to the flow of the water in our system? If we make the water pressure higher, we crank up the pressure, we push harder, what's it going to do to the flow, the current flow of that water? What's it going to do? Yep, it's going to flow faster, all right? Voltage is like that. If we crank the voltage up, we make the power supply with more volts, then the current is also going to go up. So if the voltage is increased, the current will increase. All right? And that's technically Ohm's law. That's what Ohm said. If we put more voltage into a circuit, the current will increase proportionally, is the mathematical term. So if the V goes up, the I goes up. If we make a circuit, we put so many volts into that circuit and we measure the current, and then we increase the volts and measure the current again, we can collect some data. And we could make a voltage versus current graph, V versus I, right? Please make a sketch of this graph that I am sketching for you. And if I put the volts on the y-axis, and I put the current on the x-axis, when we make this graph, it will make a nice straight line. All right? And that straight line indicates to us that this device is following Ohm's law. All right? So it means that if I started here, right, maybe I started down here. Now I got to take a look at some numbers. Let's say I started down here at a current down here of 0.05 amps. And that was caused by a voltage of 1 volt. And then I added some extra power, and maybe I added a battery, and now I have a voltage of 2 volts. All right? Then that means my current will also double and go up to 0.10. It's doubled. Okay? All right? Now, I can analyze this graph by looking at the run and looking at the rise. And remember, we did this at the very beginning where we did some math and we did some graphical analysis. What did we call it when we take the rise over the run? What do we call that property of the graph? Yep, it's the slope of the graph. Okay? Steep slope will have a high number for a slope, and a low slope will have a low number for a slope. So, slope equals rise over run. Remember that? Does that sound familiar? Nice. That's great. Isn't it great when math comes into science? By the way, science is math. Science is the application of math. Okay, now, without me using numbers right now, what is the rise measuring? What property of the circuit does the rise measure? Volts, which means essentially when I find the slope, it's volts over, what does the run measure? Yep, current, volts over amps, and what's volts over amps equal to? Danton? The R, the ohms, the resistance. This is equal to R, which means if we do an experiment where we collect some data about the way the current flows through, depending on how many volts we push, and we make a graph, and we take the slope and we calculate it, we've actually calculated the resistance. So the slope of a V versus I graph is the resistance. Okay? In this case, the rise goes from 1 up to 2. So how high did it rise? If it starts at 1 and goes up to 2, how high did it rise in that segment, Jay? It moved up by 1 volt. The run started at 0.05 and moved up to 0.1. How much did it run? Yep. See, I told you I'd forget your name. Rachel? 0.05, right? 0.05. 0.05 amps. Since we've come this far, why don't we calculate this? So in this case, the slope will be the rise, 1 volt, over the run, 0.05 amps. And what is the resistance of this resistor, or this load, whatever it is? Yep. 20, it's not joules, it's 20 ohms. Ohms. Omega. Excellent. Okay? All right? One last little thing to add to it. I am recording it. Yep. Yep, so then you guys can go back and look at it. I'm hoping I'm recording it. I'm planning that I am. As long as something doesn't catastrophically crash on me, I am recording it. Okay, one last thing. Not all things follow Ohm's law. If I have a graph of V versus I, please sketch one more graph. And again, I have the V and I have the I, and I collect some data, and I plot that data, and it does this, then it doesn't follow that relationship of rise over run. It doesn't follow Ohm's law. All right? When we get something that looks like this, we say that it is not, and you're going to love this word, but it's the right word. No, you're right, it's not linear. That's correct. But in the sense of physics, it's not ohmic. It does not have the properties of Ohm's law. It's not ohmic. If you get a straight line, then you have a a resistor that's behaving as Ohm's law states, we say it's ohmic. That's just fun to say. All right. You're going to do an experiment today where we're going to make a simple circuit, and we're going to connect a resistor into it. We're going to measure some V's and some I's, and we're going to do the same experiment with a light bulb and measure some V's and I's. You're going to make a couple of graphs, and you're going to tell me if it's ohmic or not. Question? Yep. Okay. Again, I'm going to save all this stuff. It'll end up on the site. Okay. So yeah. All right. So in a moment, I've got one more note: how to connect meters to a circuit. And you can keep writing if you've got you got everything. Excellent. Good. Let me just talk to you a little bit about the circuit. Now, if you go back and watch this video, it's just going to be me talking because I'm obviously manipulating this equipment, so it's not exciting. You could probably jump ahead. We are going to be using a power source that looks like this, all right? Now, I only have enough power sources for 10 groups, and I want to use 12. So 2 of the power sources are going to have 3 batteries that need to be connected in series in a row. So I don't care whether you use one of these or the 2 groups that have batteries in them, but the battery ones, we need to do a little bit of thinking because we're adding the batteries in a row. These power supplies are awesome because if we take a look at them, down here at the bottom, this black one right there at the bottom says DCV. We're going to be using DC volts. And not this one, but if we look up by 1, it'll say 1.5 volts, just like 1 battery. And then 3 volts, like 2 batteries. And 4.5 volts, like 3 batteries. For these power supplies, number 1, I don't have to buy new batteries, and I can just switch my electrode from 1.5 to 3 to 4.5 in order to do the experiment. You will notice that there are other connectors up here. You'll notice at the top that it says 150 volts DC. No, Robert, I see the look on your face. I know what you're thinking. You're thinking, what if? And don't do it, whatever you do. We don't want smoking wires. Everybody understand? All right, excellent. No, don't do anything. You just plug it into these. All right. You will have a handful of wires, all right, at your station. You'll have at least one and at least one black and 1 red. You may have an extra red or black. It doesn't matter what the extra one is. Connect the red one, connect the black one, which by the way is negative, to the black DC. Connect the red one to the 1.5 volts DC, all right? If you're using a battery, you'll just connect the red to the red electrode and the black to the black electrode. You then make your circuit. I'll start with the lamp. It doesn't matter which ones, but you then make the circuit by connecting it. The lamp and the resistors don't have a particular direction, so it doesn't really matter, okay? And each of these power supplies has an on-off button. On, and a little switch below it, off, okay? On, off. Some of them I don't think the light works, but you'll know when the light is on. The difficulty with the resistor is that when you have the resistor connected to it, you can't see whether it's on. On, it's doing its thing, current is running, off, but you can't tell. If you leave the circuit on for a long time, the bulb will get hot and the resistor will get hot. Right now, not hot, okay? So don't leave a circuit running unless you're measuring something. I'm going to go back to the light. Okay. So in each of our circuits, we have a negative side, the black side, and a positive side, the red side, okay? And it flows out from the negative and into the positive. That's the way our electrons flow. Now we have to connect the meters, and I want you to write this down. Now, in this particular note, all right, in this particular note, you can write measuring current and voltage. And if you are trying to draw ahead, don't. And that's because I've got kind of a really tacky animation on how to make the connections. All right? It's just a series of slides. If you looked ahead on your phone, you'll notice it's got like 50 slides. And that's because every slide adds a little part to it. It's really not much to write. So you had to wait. You okay, Jenny? Because I know you like writing ahead. All right. So let's talk about how we measure current. Now, don't worry about the homework. Remember I said back we weren't going to bother writing down the way we look at resistance on the resistors. That's if we were to do it. Let's move up and talk about measuring current. I'm going to bring this whole thing up. Don't draw the circuit yet. Write down the bullets. All right? And then we're going to write down the rules, and then you can draw the circuit. Now, we may not get this lab done today. Not a big deal. We'll continue on it tomorrow. There's a second lab that we're going to do, but we're going to do that one on the virtual circuit program that I've already shown you. And over the next couple of days, or however many it takes, we're going to work through the real circuit lab and the virtual circuit lab. But I have to show you how to connect things, because if you connect wires randomly, it can be dangerous, right? You can have a short circuit, and we want to avoid that. Current is measured with an ammeter. Now, we have different versions of meters. This is called an analog meter. It means it doesn't use computer chips and other things like a digital meter, all right? We're going to measure our amps with an analog meter. And you've already seen an analog meter when we did our little practice measurement at the very beginning, all right? I'm now going to show you how to connect the ammeter, all right? It's got a big A in the middle. We're going to measure our volts using the digital multimeter, just because it's fun to use both. We do have analog voltmeters. They're on my cart back there, but I like to use both so you can see how they both function, okay? All right. This is the one that I keep in my drawer, but you're going to be using ones like the ones that you used in the lab the other day, okay? All right. So, current must flow through an ammeter. Remember, current is the flow through the circuit, right? So, I like to think of dump trucks. Dump trucks leave the power supply loaded with gravel. They go through a load and they drop off some of their energy, their volts. They go through another load, they drop off some more, and they come back and they get reloaded. So the ammeter is like the guy at the gate of the gravel pit that counts the trucks that leave the gravel pit. So he's the person in charge of counting how many trucks per second go by. And in order to see how many go by, he's got to be right in line with the trucks. He's got to be in the path so he can see them going by. Just like a turnstile. You know what I'm talking about when you get on the subway when us country kids go to the big city? You know what I'm talking about? That thing that has the 3 bars on it, you push it and it counts you going in? Marshall? No? You haven't been to the big city? Have you ever been to Toronto and had to get on the subway? No. Have you ever been to a ball game at a Jays game? Have you ever been to a hockey game at an arena? At a big arena? All right, well, there's this device that counts you when you go in and you push it with your leg and it turns. You know what I'm talking about?
Oh, yeah.
Yeah, you push it with your leg and it turns and it counts 1, 2. Canadian Tire. Have you ever been to Canadian Tire? Yes. All right, good. Notice, that machine has to be in line with the path because it's literally counting everybody coming in. So, when we want to put an ammeter in a circuit, I've got to get it in the line of the wire. All right? Pay attention. Important part's coming here. Which means I need to, cut that wire so I can connect it in line. But I'm not going to cut the wire. I'm simply going to break the circuit and use my extra wire to finish the circuit so I can make it go in line, because it has to count the number. So I can then have my extra wire. There's my complete circuit. I break the circuit and I put it in. So the rules: break the circuit at the measuring point. So depending on where you want to measure that, you got to open the circuit up. You've got to make it become an open circuit. Now, how do we determine where to put the wires? It's got a negative and positive end as well. The black, which is called the common, because there's only one, goes closest to the black on the power supply. So this wire didn't have to be black. It could have been a red wire. There's nothing special about the wire inside of it. I could have used a red one. I would have then followed it back to the power supply. I would have observed that this is connected to the black, and I'm going to connect that to the black. Black connects to black. Okay? All right? Next, you will connect the red to one of the reds. Set the meter to the highest setting. Connect black closest to the negative, black to black, and red closest to the positive. Now, select the highest setting. I'll let you write that down. We always start with a high setting, so we don't overpower the meter with too much current. If we start on the most sensitive setting, we may cause the little lever, the little arm, to smash up against the other side of the meter. That can cause the arm to bend, and it can break the meter. Okay? So we always start with the biggest numbers, and then we work our way down. On our ammeters, you will find three settings. 5 amps. So you start on it. It's the highest. Important things happening here. 5 amps. Start on it. The next one is 500 milliamps, which is 0.5 amps, half an amp. And the most sensitive is 50 milliamps, 0.05 amps. All right? Each one has its own graduation marks. You can see it up here. And we always start with the 5. So, again, black connected to black. First, connected to the 5. I turn the power on. I notice that the meter hardly moves. I shut the power off and I move it over to 500. I turn the power on and I notice it moves just below halfway. I'm not quite to the 20. Wait a minute. Oh, no, sorry. I'm at about 150 on this. Can I go to the 50 scale if I'm at 150? The answer is no, because the maximum is 50 on that next scale. And if I'm at 150, I'm going to blow it over the top. So I stop there. I make my measurement, and I have my current. Okay? I'm going to shut this off. Okay. Yep. It would be 0.15 amps. Because remember, it's 1,000 milliamps for an amp. So it would be 0.15. All right. Okay, so here you can see my silly little animation now with all the slides. Look at what am I going to do? Oh, change to the appropriate range. Put that down there. That's important. In the end, you move until you get to the appropriate range. So now this is me, and this PowerPoint I used years ago when I was teaching physics. So here we go. Let's say we wanted to calculate the current. Oh, look at what I did. Ooh, I broke the circuit. Look at that, eh? How's that for high tech? That's exciting. Then I put the ammeter in, and I close the circuit. Isn't that awesome? Cool. It is awesome. At this point, I'll be measuring the amps that goes through the bottom of that circuit. If I wanted to measure the current going in, oh, I was going to do another one. If I wanted to measure the current going in, I could put the ammeter here. All right? Okay. Little question. How do you think the ammeter count at this location will be at this location? Yeah, it would be exactly the same. There's nowhere for the trucks to go. They should be moving along the circuit completely. So we really don't need to move the ammeter around in a series circuit. We just need to have one, because it's going to measure it where it is everywhere, because as the trucks leave, they got to come back. So it would be the same. Good job. All right. We're not going to be doing a parallel circuit in this experiment, but we are in the virtual experiment we're going to do. So did you draw that circuit? Did everybody get that circuit drawn? Draw that circuit. Draw that circuit. Sorry, I wasn't, yeah, I wanted you to hold off to the end until the ammeter was there. You don't need to put both ammeters in there, you just put one. Yep.
If you were to put two of those thingies?
Yep, two, one in here, one in here.
Yeah, would you still get the same
It would read exactly the same. Yep. Because as they move through one part, they're moving through the other part at the exact same rate. Correct. Okay. What if we had a parallel circuit? Well, if we had a parallel circuit, then there's more than one path. Remember, in a parallel circuit, you've got more than one path. So in a parallel circuit, if I put an ammeter there, notice how I open the circuit and put it there, I would have the current going past that resistor. All right? And if I wanted to measure the current going through the other resistor, I could put an ammeter there. All right? These would read differently because different numbers of amps would go down different paths. If I wanted to read the current through the entire circuit, I could put an ammeter there. So I could put ammeters in all of these different locations. Please draw that circuit. That's going to be the type of circuit that you're going to make with the virtual lab. Now those numbers will be different. Again, if you think about dump trucks, the dump trucks leave the power supply. We're counting them all. Somebody's there. Then some of the dump trucks go down one of the parallel arms, and some other dump trucks go down the other parallel arms. It's as if the traffic of dump trucks splits. There will be a mathematical relationship between them. If I numbered this as being 1, and this as 2, and this as 3, and we're actually thinking ahead, what would the relationship be between those things? What would 1 be equal to? What would the current at 1 be equal to? What do you think? We're going to learn about this later, but I'm wondering if you're paying attention. Yep. 2 plus 3. Because some trucks go forward and some trucks go down. And then they re-meet back here. Okay? But notice we've put the ammeters in line with the circuit. All right. So that's ammeters. Ammeters measure the current, and we got to put it in line. Voltmeters. It looks similar, but it's different. This is voltage. You wrote about current.
No, I meant in
You wrote about what voltage is, right? Remember, V is equal to the energy divided by Q, right? But what I'm telling you here is how we measure voltage. And it might have said in the back of our other one that we measure volts with a voltmeter. It might have said that already. That's true. Here I'm telling you how to use a voltmeter. Notice it says there, charges do not have to pass through the voltmeter. It's not that I'm counting things. In my analogy, remember the volts is the gravel on the truck. A voltage meter measures how much gravel is either picked up or how much gravel is dropped off. So it's a difference or a change in how much volts the charges carry, how much gravel the trucks are carrying. So we don't really need to get in line. All we have to do is check two spots across what we want to measure. Let's say we're talking about a circuit like this, and I want to measure how many volts are gained at this power supply. Then all I have to do is take a survey. How empty are the trucks here? How full are the trucks here? What's the difference? So I don't need to get in line. If I'm actually working at a gravel pit, I could use my binoculars maybe. Empty trucks coming in, full trucks going out. That's how much they gained. So I don't have to break the circuit for measuring volts. All I have to do is use the voltmeter to touch across what I want to measure. So I just touch across it like this. If I want to measure the volts dropped off in the battery, I touch here. I don't have to break the circuit. I've got special probes to do it. If I want to measure the volts that were picked up at the power supply, I touch here. Again, there's one that's black and there's one that's red. You touch the black closest to the black end and the red closest to the red end. So the voltmeter is connected in parallel. I'm going to bring the whole thing up and I'm just going to put that in there, right there. I'll let you write the rest. What's that? There's one more after? You want me to, there's more? You want me to put both voltmeters in there? There. There we go. Good. So, with our digital voltmeters, we will set our devices to DC. We will turn it to voltage that's greater than about 7 or 8 volts, because our devices are going to produce about 7 or 8 volts. So I'm using a 40 volt setting here. Okay? Do not break the circuit for a voltmeter. Set the meter to the highest setting. In this case, you're going to set it to about 40 volts. Will be enough. Touch the meter probes with the black closest to the negative, black closest to black. Because on our power supplies, black is negative. Red closest to positive. With a digital meter, you won't hurt it if you get it backwards. You'll just get a negative number. It means, hey, you've got it backwards. You can ignore it. Just write the number down. Change the setting to the appropriate range. Again, with our digital meters, if you have it set, you don't have to worry about it. Okay. I'm not going to put any other. I'm not going to worry about giving you the parallel one. I'm just going to stop this